Welcome to The Explainer. Today, we're diving into the physics behind literally everything that wiggles, sways, or vibrates. We're talking about everything from a massive skyscraper catching the wind to the tiny atoms that make up, well, everything. And it all boils down to one fundamental concept: oscillation.
So, let's kick things off with a bit of a puzzle. We've got two very different structures, both getting pushed around by the same invisible forces of nature.
On the left, you're looking at the Comcast building in Philadelphia. It soars over 1,000 feet into the air, a total marvel of modern engineering, built to handle strong winds, even earthquakes. And on the right, that's the infamous Tacoma Narrows Bridge from back in 1940, which literally twisted itself to pieces in what was just a moderately strong wind. So what's the deal? How can one building stand firm while another just collapses? The answer is hiding in the physics of oscillation. It's this invisible force that controls everything from a simple pendulum to, yes, the dramatic collapse of a bridge. But to really get it, we first have to understand the science of the wiggle itself.
Okay, let's get into the nitty-gritty, the science of wiggles. At its core, it's really all about understanding any kind of motion that just repeats itself over and over.
So, what is an oscillation? Well, in the simplest terms, it's just a back-and-forth movement around some central point of balance. Think about a guitar string right after you pluck it, or a weight bouncing up and down on a spring, or a classic pendulum swinging back and forth. All of them are doing the exact same fundamental thing. And how do we actually measure these wiggles? Well, we have two really simple ways to do it. The period, we call it t, tells us how long it takes for one full wiggle, one complete cycle. And then there's frequency, or F, which tells us how many of those wiggles are happening every single second. They're just two sides of the very same coin.
Now, just describing a wiggle isn't the whole story. To really get what's going on, we need to see how they act out in the real world. And it all comes down to three things: energy, stability, and what makes the wiggle eventually fade away.
And this isn't a new idea, not at all. Way back in the 17th century, thinkers like Gottfried Leibniz were wrestling with how to measure the force of something that's moving. He said, look, it's not just about how fast it's going, it's about the effect it can have. This idea led to something called vis viva, or living force, which, we now see as a very early version of what we call kinetic energy.
To get why things oscillate to begin with, we got to talk about stability. The best way to picture this, imagine a marble resting at the bottom of a bowl. That right there is a stable equilibrium. If you give it a little nudge, gravity creates what's called a restoring force that always pulls it back to that lowest point. And that pull is what causes it to oscillate, to wiggle back and forth until it finally settles.
Okay, now let's flip that bowl upside down. Try to balance the marble on top. That's what we call an unstable equilibrium. The tiniest little push sends that marble rolling farther and farther away. There's no restoring force trying to bring it back to the center, so you can't get an oscillation here. It's just gone.
This third case, same deal. It's unstable. The force only pulls it back from one side. And this is the absolute key. For something to oscillate predictably, it has to be moving around a point of stable equilibrium. Period.
But obviously, in the real world, wiggles don't just go on forever, right? A pendulum stops swinging. A guitar string goes quiet. That fade-out is caused by something called damping. Think of it as forces like air resistance or friction that are constantly stealing a little bit of energy from the system, making the wiggles get smaller and smaller until they stop.
And this is where we see some absolutely brilliant engineering. Your car's shock absorbers? They are designed for something called critical damping. It's like the Goldilocks zone. It stops the car from bouncing up and down after a bump as quickly as possible, bringing it back to normal smoothly and safely. No endless bouncing, no jarring stops, just right.
All right, now we're going to put these pieces together. And when we do, we get one of the most powerful and sometimes one of the most destructive phenomena in all of physics: resonance.
You know this feeling. If you've ever pushed a kid on a swing, you already get resonance on a gut level. You don't need to give a giant shove. No, you just give these small, gentle pushes, but they're perfectly timed with the swing's own natural rhythm. And what happens? Those little pushes add up, and the swing goes higher and higher and higher.
That is resonance. See, every object has what we call a natural frequency. It's the speed it wants to wiggle at. And when you start pushing it with an external force that matches that exact frequency, the energy transfer is super, super efficient. And the wiggles, the oscillations, they just get bigger and bigger.
And this
This is exactly what destroyed the Tacoma Narrows Bridge. The wind that day wasn't some kind of hurricane, but its steady gusts just happened to match the bridge's natural frequency. So with every perfectly timed push of air, more energy got pumped into the bridge, the swaying grew more and more violent, until the structure literally ripped itself apart.
So if resonance is that powerful, how in the world do we build things that can actually survive it? And believe it or not, what on earth does any of this have to do with Einstein's most famous equation?
Well, modern engineers have this incredibly clever trick up their sleeves. Way up at the top of skyscrapers, like the Comcast building, they install something called a tuned mass damper. It's basically a giant pendulum. In this case, it's a 300,000-gallon tank of water. It's designed to slosh back and forth at the building's natural frequency. So when the building sways left, the water sways right, canceling out the motion and keeping the whole structure safe. How cool is that?
Okay, get ready for the final twist, because this whole study of wiggles leads us to one of the most profound, most mind-bending ideas in all of physics, the deep, undeniable connection between energy and mass itself.
Let's do a little thought experiment. Picture this system. You've got a big block in the middle with two smaller blocks on either side, all held together by compressed springs. The whole setup is perfectly still. It has zero motion, zero kinetic energy. But there's energy locked away in those compressed springs. That's potential energy, just waiting to be let go.
Now what happens when we release the blocks? Boom! That stored potential energy instantly turns into the kinetic energy of the two smaller blocks flying outwards. Here's the crazy part. Physicists realized that for the fundamental laws of the universe, like conservation of momentum and energy, to still be true, there's only one possible explanation. That potential energy we had at the beginning must have been contributing to the total mass of the system.
Think about what that means. A system with more internal energy is actually measurably more massive. The energy locked away in every oscillation, every vibration, every single chemical bond adds a tiny little bit to its total mass. It's an absolutely stunning idea that mass and energy are really just two different faces of the same fundamental thing. And it's a truth that was revealed to us by the simple physics of a wiggle.